Welcome to another podcast. In this episode, we're going to be taking a look at more Laplace transform formulas, coming up with more transform pairs. And I want to start off by just reminding you that we had previously looked at the transform pair for the function 1 is 1 over s. The exponential e to the at is 1 over s minus a, because the exponential has the property that when you multiply an exponential times a function, in this case e to the at times 1, it shifts the domain of the function in the frequency domain by whatever the value of a is. If this had been negative a, then it would be 1 over s plus a instead. For this video, I want to start off by looking at the Laplace transform of the function cosine at. So I want to look at cosine having frequency a. Now, I'm actually going to use one that we've already proved. I'm going to use the exponential here, but in order to do that, I have to remind you of a formula that says that the cosine of at is expressible as e to the iat plus e to the minus iat divided by 2, because that's the formula for the real part of that complex exponential, and the complex exponential there, we can use Euler's formula to string it out, and what you'll see is you wind up getting cosine of at as a result. Now, what's nice about that is instead of taking the Laplace transform of cosine at, I can opt instead to take the Laplace transform of e to the iat plus e to the minus iat divided by 2. And the linearity of the Laplace transform says this is the same thing as 1/2 times the transform of e to the iat, e to the negative iat, which is 1/2 Laplace transform of e to the iat and 1/2 Laplace transform of e to the minus iat. I know from the work we've done previously that if I have the exponential, then its transform is 1 over s minus a, so this is 1/2 times 1 over s minus, and a is played by ia in this case. And here this is 1/2. In this case, s is s minus a negative ia. So in both cases we have 1/2, and for this particular problem it will be 1 over s minus, and typically when we do this we like to put the real part first, so s minus ai, and then plus 1 over s plus ai. And if you get a common denominator here, you're just going to multiply basically both sides by the complex conjugate. You would get the s minus ai, s plus ai to cancel in the top, leaving you with 2s in the top, or in the numerator. And in the bottom, remember, if you multiply by conjugate, you square each term. So it would be s squared plus a squared. Canceling the 1/2 with the 2, this leaves s over s squared plus a squared. And so the question is, did at any point in this process, did I use any formula which is going to restrict my bounds? And the answer to that is, when I did this, this is only true as long as s is greater than ia, which means that we're going to be fine there. Just can't, in the complex plane, if s were a complex value, we'd have issues, but everything's fine. So this is just the standard s needs to be greater than 0 that all the Laplace transforms have. Remember, for this thing to converge, s is going to need to be greater than 0. Alright? So we have a new transform pair here, and that is cosine of at. Its transform pair is s over s squared plus a squared. True for s greater than 0. And similarly, I could look at the sine of at, and sine of at, its transform turns out to be a over s squared plus a squared. And that's also true for s greater than 0. So we've actually made a lot of mileage here. We have several different formulas at work here for us. In the next video, we're going to do one more video of these, and I'm going to look at a special transform. The only function, if you look at this, that we really haven't looked at yet is a power function. And so I'm going to look at what is the Laplace transform of a power function in the next video. But these are the basic formulas which you should have memorized, and they should just automatically come to you when we're working with Laplace transforms here for the next 2.5 weeks or so. All right, thank you for watching.